Okay, it's now 2 minutes past and no new people have arrived in the last minute, so let's get started. So hello and thank you for coming to my session on secure multi-party computation. My name is Ahto and I work as a software architect in a company called Guardtime. And since my employer is a lot smaller and probably a lot less well-known than some other companies from which we have had speakers this week. So a little bit about our background. So Guardtime is a systems engineering company. We focus on data security solutions. And we were founded in 2007 in Tallinn and Estonia. And most of our engineering and development work still happens in Estonia, where the two largest offices are. We also, legally speaking, our global headquarters are now in Switzerland, and we also have offices besides Estonia in Netherlands, in the US, and a couple of smaller ones in Middle East. The company is fairly small, overall 150 employees and very tech-oriented. About 80% of the staff is really engineers and researchers. So the number of salespeople is really small. So we are really quite technology-driven. Also, for a company of that size, I think it is quite remarkable that we have an actual research team of 7 members. So this is a sizable part of the organization really is dedicated to research in the area of cryptography and data security. My own background is I have been with the company for 15 years now, so not quite a founding member, but one of the early employees. And my title is integration architect, so I mostly focus on helping customers understand how our technology works, training the customer engineers. I have also done onboarding training for the new engineers joining the company. And then trying to understand what the customer's problems are and how our solutions can fit to help them. So that's, I haven't done actual production coding in recent years. I really have been more of a specification writer and trainer. So I'm starting to feel a little bit out of place in the programming sessions in this conference. Because I don't really write production level code anymore. But I hope I still understand what that means. So I think that's enough for introduction. And let's now talk about what the session itself is about. So secure multi-party computation, what it is. So as you probably read in the program before deciding to attend this session, this is a technology or a set of technologies or a framework or actually a paradigm of computation where the premise is that multiple parties each have some data which is confidential, which they cannot share to each other. And they need to jointly compute some function that uses those confidential data items as inputs. And then how to do it so that they will jointly learn what the value of the function is without any of them exposing their private data to anybody else. So in short, they want to run the computation without revealing anything about the inputs. And then, of course, the point about without revealing anything about the inputs, this needs to be taken with a pinch of salt because getting the output might already reveal something about the inputs. So to be more accurate, that the process of executing the computation ideally should not reveal anything about the inputs beyond what can already be inferred from the output. So if there are just 2 parties in the computation and they want to know what the average of their salaries is, and of course each one putting in their own salary into the computation process and getting out the average, if I know my own salary and I know the average, I can reverse engineer or compute the salary of the other person from that output and my own input. So this cannot be prevented by whatever we do during the computation, this is impossible to prevent. But if there are already 3 people involved and we get the average, I know my own input, I know the average, but I don't know what the salaries of the other 2 persons are because they could be like equal or one could be much higher than the other, or it could be the other way around, and I have no way of telling just by looking at the outputs. So the purpose is that the process of computing this average should not reveal anything beyond what I already know, can infer from the outputs. This idea of secure multi-party computation was proposed first by Yao, a cryptographer of Chinese origin, back in 1982. And this is a kind of textbook illustration problem of the secure multi-party computation paradigm, where there are two millionaires who want to find out who of them is richer, but they don't want to reveal exactly how much money each of them has. So they want to put their own wealth into the process as inputs and get back a Boolean, left side or right side, who is the richer, and nothing else. And he proposed a specific protocol for this task in 82, and a more general version in 86 for more general computations. So this, in principle, this field of research in cryptography and in computation is quite old already. As a more practical and more recent example of problems that can be solved using this technology is tracking the stock levels of medicines across multiple supplies. So this is the illustration here is a scan or a print of a Swedish newspaper. Complaining that the article from a Swedish newspaper complaining that patient safety is threatened with more and more medications in short supply. And the problem is that when some medication is imported by multiple companies into a country, by multiple wholesalers, it is difficult for the state medical authorities to track that the overall supplies across all the importers are sufficient to ensure that patients have access to the medications. So, and since the actual stock levels, and in particular the predictions of what is in the pipeline, what are the orders that are coming in over the next few months, is considered a trade secret by the importers, then it's not so easy to keep track of how much of those medications we have and how much is coming in over the next few months, whether we should try to mitigate an incoming shortage without this kind of protocol. So this is an actual practical benefit of this kind of computation model. To be able to run this basically compute a sum over the stock levels, which are considered private, and then to compute a sum over maybe the amounts that each of the wholesaler is expecting to be coming in over the next 3 months, over the next 3 months after that, and so you can have, based on those multiple rounds of this computation, you can have a projection of what the availability of the drug is, and then the medical authorities can see that the shortage is coming and can try to mitigate it. So this is a motivating example from actual real life. And now, of course, if we already have established that this is a useful thing to have, then the next question is, how can we do it? How can we achieve those things? A low-tech solution is, of course, to find a trusted external party. So if I am not willing to let my competitors know what my stock levels and what my agreements with the suppliers are, maybe there is an external trusted party, for example, the state, some sort of state medical authority, where each of those suppliers can report their stock levels and projections to, and then the state authority can promise not to reveal my data to my competitors and my competitors' data to me, but can do the adding up of those stock levels and the predictions, and can then see if there is a need to intervene. But sometimes such a trusted party, external trusted party, is not available or does not exist. And then we can have cryptographic solutions to this problem. And to date, the three major ways of doing secure multi-party computation are first one based on homomorphic encryption, second one based on so-called garbled circuits, and the third one based on secret sharing. I'll briefly mention the two first ones and then the rest of the talk will focus on the third one, because this is one that is the least cryptographically heavy and perhaps most appropriate for the audience here, because it is more about the data structures and protocols than just relying on heavy math. And it is also most practical and most efficient for many kinds of tasks. So actual practical real-life products in this area usually are based on secret sharing. But briefly mentioning the other two, so the homomorphic encryption, this approach relies on algebraic properties of some encryption systems. And as a way of background, an encryption system consists usually of two functions. One is the encryption function, which takes a message and a key and then produces a garbled version of the message, which is called a ciphertext or a cryptogram, and which then is unreadable unless you know the key, in which case you can take the ciphertext and the key and apply a decryption algorithm and recover the original message from there. And many encryption systems, for example, DES and AES, are such that there is no algebraic structure on the cryptograms. So they are, all of them, each of them looks essentially as a random number, ideally statistically independent from the key, from the message, from any other key or any other message or any other encryption you can get from any other message. So, and in this case, there is really nothing you can do in terms of computing on the encrypted data. But some encryption systems have what is called a homomorphic property, which means that if I encrypt one message and I encrypt another message, then it is possible to take those encryptions and without decrypting, combine those decrypted states of the messages and obtain a decrypted state of what would have been if I would have first added those messages together and then encrypted the result. So the computation does not need to decrypt the data. The computation operates on encrypted data directly and then obtains from the encryptions of the input data, obtains an encryption of the output data. And then if everybody agrees that now this is the result that we want to decrypt, then this can be decrypted and revealed. But each party can take their own input and encrypt it separately, and then we can operate on those encrypted data. So that's roughly the idea. There is a ton of complications, like if I am the owner of one piece of data and my counterparty is the owner of another piece of data, can we share the same encryption key? Probably not, because then if the counterparty gets encrypted version of my message and they have the key, they can decrypt it if they are curious, if they want to break the protocol and learn my secrets. So there is a bunch of complications. You may need to use either different keys, in which case the homomorphic properties of some of the systems break down. You may need to use public key crypto systems where the encryption key and the decryption key are different, and then we can make it so that it is possible to put the inputs into the computation, but it is not possible to use the same tools to reverse encryption and recover the plain text of other people's data. So there are things you can do. And now with the homomorphic properties of encryption systems is an encryption system may have no homomorphic properties like the DS and AES. There is no algebraic structure, at least none that we know of that we know how to use in those systems. And then there are some encryption systems which are partially homomorphic, which means that it is possible to do addition or multiplication, but not both. For example, the RSA encryption system, which is oldest and most well-known public key crypto system, where the key that is needed for encryption and the key that is needed for decryption are different. And so it's asymmetric in that sense. This one that was invented in 1977 already, this is known to be multiplicatively homomorphic. So it is possible to encrypt one piece of data, another piece of data, and actually if you then multiply those encryptions, you will obtain an encrypted version of what you would have gotten if you have multiplied the messages in the first place and then encrypted. So it doesn't matter. So order of evaluation doesn't matter. You can do the encryption first and multiplication second, or you can do the multiplication first and the encryption second, and the result is the same in both cases. And this is what is called a multiplicatively homomorphic encryption system. The ELGA-MAL encryption system invented in 1985 and mostly used for digital signatures these days, not so much for encryption, has also a multiplicative homomorphic property. And there are also, we know, several encryption systems which have additive homomorphic property. So an encryption system by Benalot from 85 and from Bailliere from 99 are additively homomorphic. So you take the encryptions of two messages and you multiply the encryptions and you obtain what would have been if you had the result if you had added the messages first and then encrypted. So it's also those Benalot and Bailliere systems. They also illustrate that the operations that you do on the plain text and the operations that you do here on the encrypted text to obtain the same results, they don't necessarily have to be the same. So the result of multiplying the encrypted messages is what you would have gotten if you had first added the plain text messages and then encrypted them. So this is also often happens in those systems, encryption systems, that if you do some operation on a plain text and you want to do the equivalent operation on the ciphertext, then the actual transformations that you have to apply to the ciphertext is different. And then as soon as, pretty much as soon as RSA crypto system was proposed back in 1977, already a year later, the multiplicative homomorphic property was noticed right away. And then about a year later already there was a question proposed whether it is possible to obtain a crypto system that would be fully homomorphic, meaning that it is possible to do both additions and multiplications on the encrypted data without having to decrypt it. And this question was an open question for 30 plus years, until Craig Gentry came up with the first fully homomorphic encryption system in 2009. So it is not a simple thing to achieve the fully homomorphic encryption. And initially, the first systems, they were horribly inefficient. So the cost of doing this add function or this multiply function on top of this encrypted data was something like 10 to the 10 times more than doing it on plain text. So the slowdown, the multiplier factor had 10 zeros in it. So that was quite expensive price to pay for security. But for certain kinds of operations, like managing cryptographic keys, where the data size is small and you really want to keep the data private at all costs, maybe it would have been reasonable. There has been, of course, a ton of new research since the first breakthrough result back in 2009. And we are now on what is called like fourth generation homomorphic encryption systems, which are a lot more efficient. So they have knocked down quite several zeros from this overhead factor. I don't know exactly by heart what the best result is, but I think roughly 100 or 1,000 times slowdown compared to computing on plain text is kind of the ballpark that you can expect these days. So this is for the homomorphic encryption, and this all uses very complicated, very fancy mathematics from lattices and error correction codes and the protocols. The underlying math is quite complicated, and also the protocols, how you have to apply this math, is quite complicated. So, but yeah, this is a keyword to look up if you want to read more about this. So historically, the oldest solution proposed for this multi-party computation result is something that is called garbled circuits. which is also cryptographically not so simple, not so easy. So the idea is that the function that you want to compute on your inputs is represented as a Boolean circuit. Well, I suppose here everybody knows what a Boolean circuit is. It's basically a mathematical model of the electronics that make your computer tick inside. And then this is originally the garbled circuit protocol was a two-party protocol. So to solve this 2 millionaires problem. Later it was also generalized to more parties, but I have written down the version, the two-party version here on this slide. So the first party represents a function as a Boolean circuit and then generates encrypted values for 1 and 0 for each wire. So you get a separate value for each wire on this circuit. If the wire is 0, this is represented by one number. And if the wire is 1, so there is, like in electrical terms, there is current or there is voltage on the wire, this is represented by another number. And those numbers are generated in a pseudo-random way and encrypted, so that by looking at those numbers, you would not be able to tell which one is representing which number represents 0, which one represents 1. And then the representation of the circuit is transferred to a second party along with the labels on the wires. And then encryptions of the first party's inputs are transferred also to the second party. So basically the circuit is written down, and the values that correspond to the inputs of the first party are represented. So roughly the state of the circuit with half of the inputs known and the other half of the inputs not known is transferred. And then in a protocol that is cryptographically non-trivial by itself, then the second party needs to be, in order to be able to evaluate the complete circuit, the second party needs the input representations corresponding to its input values. But it cannot just ask for those input values from the first party, because then the first party would learn what the inputs are. If I ask for the value, give me the value that represents the value 0 for this wire, then the first party basically knows that my input is 0. If I ask for the label for... Did we lose audio? Ah, okay. So if I ask from the other party the label corresponding to the input 1, then they also would learn that my input is 1. So there is a standard well-known cryptographic protocol which is called oblivious transfer, where I am able to, the other party has 2 values, and I am able to obtain one of those 2 values from the other party without the sender learning which one I got and without me getting the other value. So out of the values x and y, I get to choose whether I want x or y. I get x and I don't get y, or I get y and I don't get x. And the one who owns those 2 values, they know that I got one of them, but they don't know which one. So this is a tricky protocol by itself. Since this is just an aside of how else you can do this computation, I'm not going to spend too much time in the details of how this oblivious transfer can be implemented. There are several ways to do it. And yeah, so oblivious is a keyword, oblivious transfer is a keyword you want to look up if you want to read up on this topic. But basically the result is that after this oblivious transfer, the second party, second person in this protocol, they have now the circuit and the representations of the inputs from the first party and the representations of the inputs from the second party, and they can evaluate the circuit, get the output value, a representation of the output value. And then the second party can reveal the encrypted output or the representation of the output, and the first party can then reveal which value, whether it is 1 or 0 in the end for each wire, that is the output wire of this circuit. So in particular in case of this 2 millionaires problem, the ones who each knows how much money they have and they want to learn which one has more but not disclose. This circuit that you have to implement is a full adder on sufficient number of bits to represent both of those values. So if you know that the total amount of money in the world fits into, let's say, 48 bits, then the circuit needs to be a 48-bit full adder, and then you just, one of them puts in their own input, and the other one puts in their own input. Their own was encoded in binary, and then they run a subtraction algorithm on this full adder, and basically the output is the carry bit of the full adder scheme. And if it is a carry, then the subtraction had a negative result. And this means that the second value was larger. And if there is no carry, then the result is 0 or positive. And this means either the values are equal or the first value is bigger. So this is an example of a kind of a way how you represent a computation in this circuit model and how you read out the result. And a lot of basically anything that can be implemented on a digital computer can in some ways, any problem or any computation can in some ways be represented as such a circuit. It is sometimes it is not trivial or is quite complicated to translate a normal computation problem into this circuit representation. For example, there is no easy way to do loops. Normally you would have to unroll your loops. But this is roughly the same way. Like if you want to do implement an algorithm as an FPGA, then you also basically need to unroll your loops and represent your computation in such a way. So this is roughly the way how to do it with garbled circuits. And this idea, yeah, like I mentioned, the task, the problem with a specific solution was proposed by Yao in 1982, and the more general solution based on garbled circuits was also proposed by Yao in 1986. So this is also quite old technology. All the encryptions that happens in this garbled circuit model, at least in Yao's standard original version, is based on symmetric encryption like DES or AES. So the encryption itself is fairly efficient, works computationally much faster than RSA or any other asymmetric encryption system. But still, it's quite a lot of machinery, and in particular for some types of functions, translating the functions into the garbled circuits is quite expensive. You can have in the worst case, you can have an explosive blow up in the size of the circuit compared to your inputs. So this is a drawback of this model. Now, the third option, which will be the bulk of this talk and discussion today, is to do the multi-party computation based on secret sharing. And the general approach and protocol of secret sharing is that each input is split into shares, basically chopped up, and the shares are distributed among parties. And so no computational nodes that participates in this multi-party protocol will know any of the values actually. Each of them has a share of each input and works with this share, but those shares are done in such a way that if you don't have the necessary number, if you don't have all the shares, or at least some minimum amount of the shares, you will not be able to recover the value that the multiple shares collectively represent. And then this computational protocol operates on those shares, and in such a way that each node by the end of the computational protocol has a share of the result, and then the shares can be revealed, published in some way, and combined to reveal the actual result. But the inputs, every supplier of the data, they chop up their input into the shares, and the computational nodes will get shares. And also all the intermediate results during computation are represented as shares. So they ideally don't leak any data about the actual inputs. And then only the final result, then the shares are combined together to reveal the actual values that they collectively represent. And now before we go to And one thing perhaps for historical notes to mention that the first secret sharing scheme was proposed by Shamir back in 1979. Shamir is Adi Shamir. It is a letter S in the RSA crypto system. So he has done a lot of things in the 70s that are sort of foundational until today. He was part of the team that invented the first actually working public key encryption system, the RSA system, in 77. And then also invented a secret sharing system, which is actually used by practical systems until today. For some types of operations, this is still the best we know how to do. So fairly fundamental result. Now, before we go into those specific computational protocols, how do you do the computation on those shares? To be able to discuss those their security properties, maybe a bit of background information of what kinds of properties we care about in security of those systems. And so the two main things is what is a security level that's a system or a protocol achieves, and what is a threat model or adversary model, what kinds of attackers we can protect ourselves against, and what kinds of things we have to ensure by some other means that those kinds of attacks don't happen, or we just have to accept that we know this is a limitation of the protocol. And for the security levels, the two fundamentally different levels are computational security and information theoretic security. And computational security, if a cryptographic protocol has computational security, this means that breaking it is computationally hard. Breaking the security properties is computationally hard, but it is not impossible. So if your opponent has a sufficiently powerful computer, there is a way for them to use this computer to break your security. So for example, if we are talking about encrypting with DES, then the encryption key size in DES encryption system is it is represented as 64 bits, but actually 8 of them are checksums, so they don't contribute to the number of possible keys that an opponent would have to try in order to just brute force your encryption system. So the effective security level is 2 to the power of 56. The effective number of bits in a DES key is 56. So in the worst case, your opponent has to try 2 to the power of 56 possible keys, apply each of them to try to decrypt your data, and then check if the result looks like something that might be your input. And if it is, then they have found your inputs, they have broken your encryption. This kind of thing. So for AES, the keys are much longer. So the amount of work that the attacker has to do to perform this kind of brute force attack is much larger, but there is a limit. Since the keys are finite length, if the attacker is able to just try all the keys and decrypt your private data, then they are able to eventually get your private data. Now, of course, if the attacker has to do something like 2 to the 100 or 2 to the 200 operations, then just the number of operations is so big that the universe will burn out. We will have the heat death of the universe before this computation finishes. So in practical terms, we perhaps don't care. Doesn't happen any time in any meaningful time frame. So any time longer than certain amount you can consider it equal to infinity, especially if the expected time of cracking your security is longer than the lifetime of universities, and really the large number and the infinity, they are, for all practical purposes, they are indistinguishable. But in principle, the computational security means that there is a mathematical equation between the inputs and outputs, and an attacker who is able to solve this equation will be able to get your input from the output, or if the attacker is able to observe messages that different parties exchange in the process of this computation, and there is a relationship between inputs and those messages, then the attacker will be able to recover the inputs. after solving this equation. And then the question is how much work it is to solve the equation. If the work is sufficiently large, your system is secure. If the work is too small, then your system is insecure. And how much is sufficiently large depends on how confidential your data is. If it is like state-level secrets, you can expect state-level opponents with state-level budgets, and they can do a lot of computation on a state-level budget. If it is just you sending messages with your mate, and you don't want I don't know, your girlfriend or another member of like a classmate to snoop on your messages, and of course the barrier is much lower. So your classmate probably is unlikely to spend more than half a day of computation time to crack your message, because by the time he cracks a message, the meeting that you had in secret has already happened, and learning the location and time of that secret meeting with your mate after the fact really is probably not a security risk anymore. So these kind of things. And then on the other hand, there is a thing called information theoretic security. And this is a level above. This means that there is no equation relating the inputs to the outputs. So there is no computation that the attacker could perform to break the security of your model. So basically, by observing, it is if a protocol has information theoretic security against some types of attacks, this means that it is impossible for an attacker of any computational, even of infinite computational power, to break the security of the system. And it might sound impossible, but there are actually some cryptographic systems where some of the cryptographic properties have this information theoretic security level. So that's, I think philosophically speaking, that's a strange result by itself that this kind of thing is even possible, but it is. Another way to look at this is more on the operational side, what we expect the adversary to be able to do. A multi-party computation, which is said to be secure in a passive model, or also this is sometimes called an honest but curious model. If it has the properties that somebody who, when the parties of the protocol exchange messages, when somebody observes the communications between the parties, that they are not able to recover the secret inputs. But another level is active security, or security against active adversary, which is able to also forge and suppress messages as they want. So to actively interfere in the process of the computation. And if they can reveal the secret inputs in this case, then it is said that the protocol is insecure in this active adversary model. A good way to think about those passive and active adversaries is maybe not so much as a god level person who can see everything, but to model this in your head in practical terms. If an adversary is able to plant malware in one or more of those nodes that participate in the computation, what can they do? So if the malware can only observe traffic in and out of that node, can they learn the secrets from the other parties? Or if the malware is able to change messages or send out forged messages, can they trick other parties into revealing their secrets? So this is perhaps in practical terms, this malware installed at my server interfering with how my server participates in the computational protocol. This is perhaps a more practical way. And this way also both the passive and active security can be also, they can be quantified. How many nodes out of the whole set who are participating in this protocol, how many nodes I have to corrupt before I can learn the secrets of the other parties. So this is the models, how we discuss about security and how we measure how secure protocols are against different kinds of attacks. And so now actually looking at what the protocols are and how to do those computations. Okay. So the first one, the simplest way to do secret sharing is to split a value v. This is my input into the computation, and if I want to split it into shares, so the intention, just to remind you, is that I am the owner of some input, and then there is somewhere is a network of nodes who will do the computation, and I will give inputs to the nodes. And usually the security model is such that each of the parties controls one node, so they can be reasonably sure that at least one node is honest and is out there to protect. So if I run one of the computational nodes, I can know this one is on my side. It is out to protect my interest, my secrets. And likewise, other parties probably will want to run each of their own nodes. And then collectively, we have a number of nodes, which will then engage in this multi-party protocol. And it is for modeling the protocol and also the security properties, it is often useful to distinguish me as a data source and the node that operates on my behalf. Because me, I know my input. But even to the multi-party computation node that represents that I run in this protocol, I will only give one share of my secret input. So it is easier to model the security properties of the protocol in this way because we can treat all the nodes as uniform. We can expect that each node has one share of each input, but just because I run this node, it doesn't mean that the node knows my full input. It's more uniform and it's easier to reason about the security properties. And so it's usually modeled in this way that I as a data owner and the nodes that I operate as part of this multi-party computation protocol, they are separate entities and they have different knowledge of the inputs. So in order to split my value to be submitted into this network for the computation, to split it into n shares when we have n nodes participating in the protocol, I do it like this. I first pick n-1 completely random values from some range. And then I pick the last share such that when I add up the shares modulo this some large number, then the remainder of this addition when divided by the modulus, this is the value that I want to be represented. So this is a standard modular arithmetic. Everybody knows it. We use it daily on the watch. We use it daily in our unsigned integers, where everything happens modulo 2 to the 32 or 2 to 64, depending on how large CPU you have. So this is how it happens. For certain mathematical properties in cryptography, it is often useful that the modulus is not actually a power of 2, which would be very convenient for our binary hardware, but the modulus often needs to be a prime number for some of the mathematics that we use later to work out correctly. So this is maybe an inconvenience, but you have to live with it. And the modulus also has to be large enough. It has to be larger than the largest possible input. And in general, it is also useful that the modulus is larger than any of the intermediate values that occur within the computation during the computation, and also that it is larger than the output we want to compute in the end. So otherwise, if your modulus is too small, then you will not be able to distinguish. Like if your modulus is 12, then and you do the computations mod 12, then you will not be able to distinguish between the value 6 and the value 18, because if you take the remainder of dividing those with 12, they both are represented in your system as the value 6. And you would not be able to. This is a classic overflow problem. You try to stuff a value of 6 billion into 32-bit unsigned int. It comes out on the other end as 2 billion, and you have lost some of your information. And you will not be able to tell the difference if the original value was actually 2 billion or if it was 6 billion. So it is the same problem here. And additive secret sharing by itself is known to be information theoretically secure with any set of any incomplete set of shares. So if you split your input V into n shares, and then somehow the adversary manages to collect n-1 of those shares, they will learn exactly nothing about your input. because the final share that they don't have could be any of the values from 0 to m-1, any one if any of them is equally unlikely or equally likely, then basically if the last share is for any possible values of what the v initially was, there is a value of what the last share could be. And if you don't know what the actual value of the last share is, you have no idea what the original input value was. So this is you get perfectly uniform distribution of possible input values relative to the information that the adversary knows. So they get no clue whatsoever what the actual value could have been. Except for what they already know, like if they know that this value represents somebody's salary, and they know that nobody gets $1 billion salaries, and of course they know that the input value could not have been $1 billion. It definitely was something less, but they know it from outside. They do not learn it from the pieces of information that they collect in this protocol. And this is what the information theoretic security means. Even if you get to see those shares, you learn absolutely nothing about the value that those shares represent unless you have all of the shares that you need to recover the value, and then suddenly you know the value exactly. So there is no gradual level of security. You lose one share, you lose all knowledge about what the shares represent. It's also interesting that it is clear that if you pick those n-1 first values randomly, uniformly from 0 to m-1, then those are uniformly distributed. There is no bias, there is no value that is more or less likely unless your random number generator is broken, but then you should not use it for cryptographic purposes anyway. But it's less clear that since you pick the last value, not randomly uniformly, but you pick it based on an equation, it is less clear whether the last value might have a bias in it. But it turns out no. This is also, if the others are uniformly distributed, then the last one is also guaranteed to be uniformly distributed. So there is no bias, there is no statistical inference that an attacker could do based on the value of this Vn of this share either. So very, very nice and cool properties. Now, adding, if all you need to do in your protocol is adding stuff, like when you want to compute the sum of the stock levels, or when you want to compute the average of salaries, then basically the only thing that you need to do on the secret inputs is adding. And in additive secret sharing, adding is trivial. So if you have a value v1 represented as 3 shares and value v2 represented as 3 shares, then and those shares are distributed among 3 nodes. So the first value split between 3 nodes means that this value goes to the computational node 1, this to node 2, node 3, and then adding can be done component-wise. So the first node that has the 2 shares can just compute the share of the sum. Second node locally can compute the share of the sum. Third node can locally compute the share of the sum. And it is then the sum of the shares represents the sum of the inputs. So this is quite easy to also represent graphically. So we have now here, this is a model. We have the data source, which knows the actual input value. And here are the 3 nodes. So basically each of those nodes is operated by one of the data source. And then for ease of representation, I have added an extra kind of coordination node or summary node, which collects the answer. In practice, oftentimes this does not exist as a separate node or element in the system, but those nodes collectively implement this summary node. But it's the arrows that I want to draw next would get quite messy if I didn't have this as a separate entity on the figure. But this is more of a logical, not a physical node, usually in those protocols. So the first, the source of the first data splits it into shares, gives 1 share each to the computational nodes. Second source of input does the same. Each node gets 1 share of the input. Third one does the same. And now what we have is that this first node has 1 share of each input, but doesn't have the whole input of anything, any of the whole inputs. Second, the same, and they can then compute the shares of the inputs locally. This is a local operation. They don't need to even to talk to each other. So in a sense, this is not even a distributed computation in this case. It's just every node is doing a simple operation locally, and then those shares of the result can be sent to the coordinator node, and the coordinator node can recover the final answer. And the important thing here is that none of the intermediate results that are available here in those nodes can be, if the attacker is able to corrupt one or maybe two of those nodes, they will still not learn the inputs, because for each input they are missing one share. And because of this security property of this secret sharing model is that if you have just 2 out of 3 shares, you will learn nothing about the actual inputs. So this is the security model we have here. Then one thing that you of course need to remember for security is that the attacker, they cannot learn the secret inputs, but if they actively corrupt the nodes here, they can spoil the result. So if instead of the correct value, which is the sum of the shares, an attacker who corrupts this node sends some random number, then instead of the correct value of S1, the random number is put into the sum, and then of course the sum that comes out is bogus. So this protocol is secure against passive adversaries who want to learn the secret inputs, but it is not secure against active adversaries who want to spoil the computation by spoiling the messages that are sent from the computational nodes to the summary node. And another thing that is important to remember is that any of the multi-party computation protocols, even if they are actively secure, even if they are secure against nodes being corrupted to send the wrong messages or to do the computations wrongly, to misbehave in this way, none of them can cryptographically protect against a malicious input party. So if my actual stock level is V1, but what I do in this secret sharing step, if I share a value that is not actually V1, but I lie about my actual stock levels here, then of course nothing that happens here in the computation protocol later can recover from this error. So if the input is wrong, the output is also going to be wrong, and no cryptography can fix that. This can only be fixed by auditing, by sending an auditor to see whether the stock level, actual stock level matches what is in the inputs. So this is a different problem that the computational protocol cannot solve. We can only ensure that the output is correct if the inputs are correct. If the inputs are wrong, then all bets are pretty much off. Now, multiplying with additive secret sharing is a much more complicated proposal, because if let's suppose I have a value x, which is represented as 3 shares additively, and a value y, which is represented as 3 shares additively, then what happens if I want to compute the product of them? Well, the product x times y is this sum times this sum, and if I open the parentheses here, I get those 9 terms. And out of those 9 terms, the blue ones on the diagonal are such that x1 and y1 are owned or handled by the same node. So this multiplication can be done locally. Those 2 are handled by the second node. Again, you can do this. Those are handled by the third node. You can do this. But also red ones, they are problems, because x1 one node has, x2 another node, y2 another node has. And now in order to compute this multiplication, one of the nodes would need to send its secret share to the other node. But this would be, to do it in a naive way, would be problematic, because if node 2 would send y2 to node 1 in order to do this product, and node 3 would send y3 to the first node in order to do this product, then the first node would have y1, y2, y3, all 3 of them. And he would be able to recover, it would be able to recover the secret input, which was something that was not supposed to happen in our protocol. So how do we fix this? So first thing is already bad enough that the nodes have to communicate with each other, because this is overhead. But the major problem here is that by doing it in a naive way, we would break all of our security promises. no good. So what is the solution, which is the basis of a multi-party computation platform called ShareMind? What they do in this? They do something, an operation called resharing. So they change the shares in a specific way in some ways, the resharing part is really not so. Maybe I should have split this in 2 slides and explained it in 2 steps. But now, since a mistake has already been made, let's try to recover from here. So the multiplication part actually is what happens here in those 2 lines. And what is a party 1? So the idea is that the first node has x1 and y1, the second node has x2 and y2, and the third node has x3 and y3. And in order to prevent any of the nodes from having all 3 shares of any of the secrets, what we do is that the first node sends its secrets to the second node. So now the second node has shares number 1 and 2 of each secret. The second node sends its shares to the third node. So now the third node has shares number 2 and 3 of each secret, but still is missing 1. And the third node sends its shares to the first node. So the first node now has shares number 1 and 3. And is missing still share number 2. So none of them can still recover the secrets. And now each of them has enough inputs so that we can distribute those things, those 9 things that we can compute. We can distribute among the nodes in such a way that each node computes with only those shares that they have. But in the end, we get all those 9 elements that we need. So we can compute a share of the first share of the product in the first node by combining only shares indexed 1 and 3, which we have in this node at the moment. And in the second node, only combining shares number indexed 1 and 2, and then here only shares indexed 2 and 3. And this is it is easy to verify that this actually contains all the components we need of the product. And now the problem with doing this is that now each node has more shares than they were initially having. And if we do another step of the computation, it might easily happen that with the 2 steps combined, some node will have all shares of some secret value and will be able to recover the secret itself, which shouldn't happen. And now this is where the resharing happens. So basically, before and after each multiplication operation, we do a reshuffling of the shares. So during this multiplication operation, temporarily, the first node has the shares indexed 1 and 3. But after that, we do a resharing operation. And then again, first node only has a share indexed 1, second node has only share indexed 2, and the third node has only share indexed 3. And this resharing is done in such a way that each of the nodes generates a random number and sends it, or wrong button, I'm sorry. Where was my, here. I wanted to use a pointer. So it generates a random number and sends a random number to the next node. And each of those nodes then after this shuffling around of the random numbers was done, then each node adds one of the random numbers to each share and deletes, subtracts the other one. So there is 2 random changes, but the random changes are synchronized in such a way that this R12, which is first random number, so this is added to one share and subtracted from another share. And this happens with all of those random numbers, so the total doesn't change. But each of the shares now contains randomness from fresh randomness from 2 sources. And whatever correlations was here temporarily during this multiplication protocol, this is now erased by adding those random numbers into the mix again. And it is always secure to do it in this way, that you do the resharing, you do the multiplication, and you do the resharing again. In practice, oftentimes, if you do multiple multiplications in a row, you can, of course, reshare and reshare. If there are 2 reshares in sequence, you can do it just once as an optimization. But basically, in principle, this is how you can do. Now, you can do both additions, which is a simple local operation with no need to communicate between the nodes, and you can do multiplication. And basically, you can, if you can do those two things, then any arithmetic expression you can compute. And if you add a little bit of more complication to do comparisons, then basically you can express any computation. And this means that in this model, you basically have universal computability. Anything that can be computed in this model. Some of it might be expensive because if you need to do a lot of multiplications, you need to do a lot of communication, a lot of random number generation. So it might be expensive. You might need to work to reduce the number of multiplications in your computation and replace them with additions as much as possible. But in principle, you can run any computation on this protocol, on top of this protocol. Now, I already mentioned that this kind of resharing-based multiplication is what the product called ShareMind does. This is a product of a company, Cybernetica. In the interest of disclaimer, I have friends working in this company, so I am maybe a little bit biased to advertise them here. I have no economic interest in the company. I'm not a shareholder or anything. But yeah, you can look up if you want to read more about ShareMind specifically. You can look up their website. Currently, as far as I know, when I last checked, they only support 3-node multi-party computation protocol. So even if there are more parties giving inputs, the number of nodes that runs a computational protocol is always 3. What is maybe especially appropriate, why it is especially appropriate to mention ShareMind in this conference is that the computations are programmed in a dialect of C. So they have taken the standard C programming language and added extensions to this language to express that some values are normal values. They are not secrets, they can be just given to the nodes. And some values are secrets, so they have to be given to the computational nodes as shares. And then the compiler takes care of doing all of this secret sharing, shuffling, resharing in the background. So you as a developer, you just say that this is a normal integer and this is an integer variable containing a secret input. And all of this sharing and shuffling around of the shares is taken care of by the compiler. And this was implemented as a fork of GCC. So they took the GCC compiler and added extensions for those secret share values into GCC. And otherwise, you write your computation as a normal C program. Now, in the interest of completeness, I should also mention another popular protocol for doing these kinds of computations, which is also based on additive secret sharing. And it improves the multiplication speed during the computation by pre-computing. So in the speeds protocol, the nodes, before they get the assignment, now compute. They can, while the nodes are standing idle and waiting for the next computational request to come in, the next task to come in, they can prepare. They do a pre-computation of shared triplets. So basically they do a bunch of triplets of numbers A, B, and C, which has the properties that C equals A times B. And then they do, when they have generated this random triple, they do a secret sharing of this triple. And it is, again, cryptographically a bit involved. How do you generate such triples in such a way that nobody learns all the inputs? So basically, A is generated in such a way that each of the nodes generates one share of it. B is generated in such a way that each of the nodes generates it. And then C is computed as a multiple of them among them. But the trick here is that the ABC values can be pre-computed without knowing what the computation is that you will do next. So you can do this in sort of offline setting while there is no client waiting for you to respond. And then if you have supply of those triplets, then the result is that when an actual computation request comes in, through another clever trick, you can do multiplications also basically as local operations. You don't need to communicate between the nodes for each multiplication separately. And so the actual computation can run faster. The speeds protocol also adds more cryptography to obtain active security. So even if some of the nodes start lying, then the other nodes can detect this. And so you have more assurance about the correctness of the results that you come out. If you want to read, the original paper is available online. The paper that describes both the multiplication protocol that I mentioned here in this point, and also how they obtain active security. But this is a little bit too much. I was correctly estimating that I wouldn't be able to fit in my time slot if I started to explain all of this in detail. So there is also a bunch of open source implementations of versions of this speeds protocol. So there is Fresco, MP Speeds, and Mamba at least, probably some others. Some of them are more commercial, some of them are more academic. The last one, this is from a university, and the first two ones, I don't even remember off the top of my head what type of organizations are behind those. But this is open source. You can just take and play around with them and see for yourself. The ShareMind things also, at least some of those things, some of their things are also open source. You can test and play around. You don't have to have a contract. Now, the next thing I want to mention is another type of secret sharing. Instead of just doing splitting your secret values into sums, you can do more clever things. And this is actually the secret sharing mechanism that Shamir proposed back in 1977. So we're catching up to what the scientists were already figuring out, 35 years ago? No, more. I can't do math anymore, sorry. So the idea is that in order to split the value into shares, you do a little bit more complicated thing. You represent each value as a polynomial. So you put the values that you want to represent into this constant member of or constant factor of the polynomial, and then you generate the other coefficients for the other powers completely randomly. This all happens again in modular arithmetic. So all of those, this value is from 0 to m-1. This is from 0 to m-1. This is from 0 to m-1. And so you can generate them completely uniformly. And of course, all the powers and the intermediate values all will be because of this modular arithmetic, all of them will be of fixed size or a limited size. So you don't get an exponential blow up because you have an x to the power of k here, or even k minus 1. And the idea now is that shares will be the values of this polynomial. So this is the picking of the polynomial is something that the data owner node does before sending the shares out to the computational nodes. And then each node gets a share, which is the value when this polynomial is evaluated on a fixed input or a fixed argument. And it's cryptographically or mathematically speaking, it is only required that the values are different from each other, so that no two nodes get the same share. And that the argument, sorry, wrong button again. And the argument, so each of the data, so the argument has to be the same in all of the shares that the node number 1 receives. And the argument has to be the same in all of the shares that node number 2 receives. But of course, the easiest way to satisfy both of those requirements is to just use the number of the node, index of the node, as the argument and do those shares. And then now the idea is that if you have a polynomial with k coefficients, including then k minus 1 of those randomly generated ones, and then the last one, which was actual values that you wanted to represent. If you have k shares, then this means that you can construct k linear equations on k unknowns. You can solve this system of linear equations, and you can recover all of those coefficients. And then you can evaluate the polynomial on the argument 0, which cancels out also all of those members here with the X in them and gives you back the original value that was shared. So this is how you do recovery of the value if you have sufficient number of shares. And again, this system also has information theoretic security. So K shares are sufficient to recover the value. K-1 shares give you absolutely nothing. Any of the M values of V are equally likely if you have less than K shares. You have no idea what the actual value could have been. And then the standard ways that anybody who has, probably anybody even who has been to high school, but anyway, anyone who has gone to college into any technical field, they know you can do this system of linear equations. You can solve it using the Gaussian elimination method. It has cubic complexity. Less people know that it is, if you specifically want to recover this value, you can do it with so-called Lagrange interpolation, which only has quadratic complexity. So in practice, all the systems that implement summary secret sharing, they do it with a Lagrange interpolation to save on computation. But from security point of view, of course, it doesn't matter. It is only the implementation efficiency. And now, unlike the naive additive sharing that we described on the couple of previous slides, this Shamir secret sharing provides redundancy. You split your secret into n shares, but you only need k shares to recover it. So if some of the nodes, if you run the computation and somehow you don't receive all the shares of the output, you can still, if you receive enough of them, you can recover the output. And also because you now have redundancy in the outputs that are provided by the computational nodes, you can start doing error checking and error recovery. If you receive more than k shares, you can see if I take one subset of k shares and see what the answer seems to be, and if I take another subset and third subset, all the answers are all the same. Roughly speaking, this is how you can do checking. And if the answers are not all the same, then depending on which subsets agree with each other and which ones do not, you can also discover which of the nodes is lying to you. Whether it was by accident, whether they had a glitch in their computation, or whether it happened by malice, whether they did it on purpose. This is a different story, of course. You need a separate investigation into that. But you can at least verify that with the redundancy, you can verify that there is no errors in there. So if you have more than k shares, you can do error checking and recovery. With computing with Shamir secret sharing has problems similar to computing with naive secret sharing in the sense that if you have x shared as one polynomial and y shared as another polynomial, then adding is trivial. The sum of x plus y could have been shared or can be represented as a polynomial, which is the sum of the two polynomials. And this means that the shares of the polynomial representing the sum can be computed locally. So if you think about what it means to add two polynomials, you will see that this adds up. So adding is trivial, just the same as before. Any node to compute their share of a sum, they can just add together the shares that they have of the addends, and the result will be correct. And also the resulting shares will be uniformly distributed, so it is both correct and secure to do addition in this way. In Shamir secret sharing, this is no problem. Multiplication in a way looks trivial also, but this is deceptive. You may notice that if you want to compute z, which is a multiplication of the two inputs, then as far as polynomial multiplication goes, this is correct. You can do the multiplication of two polynomials, and you can obtain a polynomial that represents the product of the inputs. And it would also seem that you can compute the shares of this polynomial by just multiplying those shares, but there are problems. First, the degree of this multiplication polynomial is higher. So in this case, having k shares is no longer sufficient to recover the polynomial. And this means that if you just do this in a naive way, then you actually have no idea what the product is, because you don't have enough shares recover the value of the product. A minor problem compared to that you don't know what the answer is that the shares of this this coefficients of this product polynomial are not uniformly distributed anymore. So a very determined adversary might be able to use this bias in the distribution of the coefficient values to infer something about your data if they are able to observe many of those values. So in order to counter those two things, you need to perform a multiplication, you need to execute a so-called degree reduction protocol, which basically takes those two polynomials as inputs, as shares, and gives you out polynomials, the shares of another polynomial that represents the product correctly, but it is not the same as just multiplying those two polynomials together. So the resulting polynomial is guaranteed to be of degree k-1. So again, k shares will be sufficient to recover it. And it is also, if you do the degree reduction protocol correctly, it is also guaranteed that the coefficients of this new polynomial will be uniformly distributed. So again, having just a few shares will give you even no statistical indication about what's the distribution of the actual value or what's the probability of different represented values could be. Again, this protocol, you can look it up. It is a bit too complicated to fit in the time here and to fit on the slide here. But as a mention again, there is a product called Virtual Data Lake, which is from Roseman Labs, which is another company where I know some people who works there. So here's your disclaimer again of my bias of mentioning them specifically. They do distributed computing and multi-party computation solutions based on Shamir secret sharing. So they might also be worth checking out. As far as I know, their stuff is not open source. So if you want to play around or have a demo, you actually need to talk to the salespeople, and then they can organize a demo for you. So you cannot just go to GitLab and look at what they have, unlike some of the other projects that I mentioned previously. Now, in the last 10 minutes that I have, I want to quickly also plug a product of my own employer. So here is your disclaimer on bias again. The multi-party computation products that we do is not a general purpose one. It is solving a specific problem, more specific, more specialized protocol for a more specific problem. And the more specific problem is called private set intersection, where the thing that you want to compute is, or the setting is that each party has a list of values, and they jointly want to compute the union or intersection of those lists or those sets. So this is not as generic as doing any kind of arithmetic computation on one hand, so it's less general, but on the other hand, it is a type of problem that is quite inconvenient to do in the other models. It is, in particular, this kind of problem is, or this kind of task is very hard to express as arithmetic function, and therefore it is very hard to do as circuits. So all of those arithmetic circuit-based solutions are already out. And it also has practical applications, which is why a commercial company is doing this kind of thing in the first place. And one of the applications is so-called outcome-based pricing, where some certain expensive drugs, and especially expensive and narrowly focused drugs, where there are not enough patients to do a large-scale medical study to be sure that the drug works for all the patients. And because drugs are specialized, they tend to be expensive. So insurance and hospitals are reluctant to pay for them if they don't know for sure if they work on any specific patient. And so the idea is that the hospital who is or a pharmacy or the insurance who is paying for the drugs for the patients, they have a list of patients who have been treated with some drug. And then a hospital or an ER might have a list of patients who have been to the emergency room with a specific diagnosis. And having this diagnosis and having this emergency room visit is a proof that for this patient, the drug actually did not work. It did not prevent the next attack of the disease. And then for those patients, the insurer might want to get the money back from the drug manufacturer, for the pharmaceutical company. But in many countries, the insurers, the hospitals, and the pharmacies are not allowed to share this data with each other. And so this is a place where this private set intersection protocol can come in handy. So we have a pharmacy or the insurer knows for which patients they have paid for this drug. They have covered the cost of this drug for those patients. And we have a list of patients for whom the drug did not work. And now the hospital that is running the ER room and the insurer or pharmacy, they can jointly compute what is a list of patients or what is a number of patients for which the insurer needs to get the money back from the pharmaceutical company. So that's a setting. And roughly, yeah, like I mentioned, this is a product of my employer. Roughly, the idea is that we employ an encryption system which has a different property from the homomorphic properties that we discussed before as a more general case. This is based on the commutative property that some encryption systems have and some don't. And the idea is that if you take a message and then encrypt it with one secret key and then encrypt it with other secret key, so you do a double encryption. And in most cases, the double encryption is sensitive to the order in which the keys are applied. So if you encrypt with key 1 first and key 2 second, or if you do it with key 2 first and key 1 second, most of the encryption systems will give you different results. But there are some in which it is guaranteed that for every message and key 1 and key 2, those two are the same, independent of the order of the encryptions applied. And this means that we can build a simple multi-party computation protocol on top of that. So the first party gets a list of patient IDs and encrypts each ID on this list with its key. So if it is an insurer who has key 1, then each patient ID gets encrypted with key 1 first. And then this encrypted list or this list of encrypted identifiers is sent to the other party. And then the hospital that runs the emergency room gets a list of patients that were in the emergency room and encrypts each of those IDs with their own key and sends this list of encrypted values to the pharmacy. And now each of them takes a list that they received, which has already been once encrypted, and encrypts it again with their own key. So in the case of the pharmacy, which was encrypted first by the pharmacist's key, it gets now encrypted with ER room hospital's key. And in case of the ER room, which was first encrypted by the hospital's key, it now gets encrypted again with the pharmacist's key. And if there are matches in this list, this means that there were patients who were in both lists. And that's the answer that you want to get. You can do either the list of the encrypted patients, and if there is sufficient agreements in place that for those patients who are in the resulting lists, they can be decrypted, and they can, again, jointly, they can agree that those patients were in both lists. They are in the answer set. The decryption can be applied in layers also. The identifiers can be recovered, but in some cases, even the identifiers never need to be recovered because only the number of patients for which the money needs to be paid back is relevant, at least as far as financial dealings are concerned. Of course, for patients themselves, if they were in the ER, then for the hospital that was treating those patients or the doctors that was treating those patients, the identities of those patients are also important to look for other remedies for their illness, given that this drug did not work. But this information can be handled in another way. This is mainly about the financial dealings between the insurer and the pharmaceutical company. And it is a good idea to preserve the privacy of the patients in this setting, because identities of the patients do not matter in the financial terms. There is, in the last couple of minutes that I still have left, there is another layer that we can put on top of all of this is a verifiable multi-party computation, where with all this privacy and secrecy in the secure multi-party computation, it is possible as a side effect of the computation to also produce a proof that the computation process was carried out correctly. If you don't know what verifiable computation is, then this is basically a set of tools and cryptographic protocols to check that an untrusted party who was asked to execute the computation did the computation correctly. So it's like outsourcing your computation work to some service provider and then verifying that the computation was done correctly as you asked. I did a talk on this last year. I do have to give a warning that the last year's talk was a lot heavier on mathematics. A lot of it is really, if you don't if you don't have a degree in mathematics, you probably are very. It will be very hard for you to follow the mathematical details. But if you just want to get an overview of what is possible in this kind of thing, then maybe you want to skim this talk. And in the context of multi-party computation, then each party, if you do this verifiable multi-party computation protocol, if you combine those things that we discussed about today and the things that I talked about last year, it is possible to obtain such a protocol that each party can verify that all the other parties behaved correctly, that they executed their part of the protocol as they were supposed to. And an outside recipient of the result can also verify that the whole computation was done correctly. And for this, kind of thing, there are a few experiments. I don't know of an actual product that would do this in real life, but there are some experimental things. In particular, there is a multi-party computation library written in Python. So basically, the idea is that you can write your functions that you want to compute in Python, and it will get executed on in a multi-party computation setting, much like the C-like code was done in ShareMind. This is an academic work by a researcher from Eindhoven University, MPIC. And this one is doing the normal secure multi-party computation. And there is a private research prototype, which, as far as I know, has not been yet published, which then combines this multi-party computation thing with a verifiable computation thing to obtain a protocol which runs a multi-party computation and produces a proof that the protocol was executed correctly. So if you are feeling like you're really interested in this kind of thing and want to try it out on the very clear warnings that this is a research prototype and not fit for production use, I can give you an intro to the author and the verifiable computation part was done by another person, not the author of this MPIC, the original MPIC. So this is a fork done by another researcher. So I can give you an intro to the author of this thing, and maybe you can work out an arrangement of you playing with it and giving feedback and so on. And that was, I'm out of time, and luckily I am also out of slides. So thank you for your time and attention. If you have any quick questions. The question was, what is the overhead of secret sharing compared to simple computation? The secret sharing itself, really, the overhead is very small. So it's if you do a three-way secret sharing of an integer, then adding those shares means that you do the addition of each share separately. So it's like a 3 times overhead. The main problem is with a multiplication, where unless you do the speeds protocol, you need to communicate between the nodes. And even if you do the speeds protocol just moves the need for communication or moves the communication cost to another place. Because in the speech protocol, during the actual execution of the multiplication protocol, the nodes do not need to talk to each other. But each multiplication consumes one of those ABC triples, which was generated before by basically executing a multiplication computation in advance, in preparation of this triple. So this means that for each multiplication in those protocols, you will incur a network call. And so this is the main thing in the overhead. The computational overhead, I think, is trivial compared to that the nodes need to talk to each other over network for each multiplication that you execute. That is the main thing. But this overhead only happens when you multiply two confidential values. So addition of either confidential or public values is pretty much free, and multiplication of a secret value with a public value is also free. The only thing that is expensive is multiplying two secret values. And there the overhead is basically two round-trip network calls and network round trips, roughly speaking. So, but a very relevant question, yes, for practice, of course. What is overhead? Any other questions? If not, then thank you and enjoy your lunch.